Do I need to be liked? Absolutely not. I like to be liked. I enjoy being liked. I have to be liked, but it's not like this compulsive need to be liked, like my need to be praised. Well, let's go ahead and take a look at some lines and planes. And specifically, we want to understand how we're going to represent lines and planes in 3 dimensions. So you know how to represent a line in 2 dimensions. And so the way that you would do this is using either y equals mx plus b, or you could represent it parametrically as y equals a times t plus b and x equals c times t plus d. Now, I know that's a bit of a stretch because really, when I say that uh, you know, could represent it this way, you probably have never represented it, a line this way in 2 dimensions, but you could. So the issue here with 3 dimensions and with this business here is that in 2 dimensions, so the way that you learned lines is you always have a direction, and the direction tells you the slope. The slope tells you the direction the line is going. And then this thing tells you a starting point. So that's the y-intercept, and it tells you a starting point. Anyway, in 3 dimensions, you have a similar situation. We're going to have a starting point. That starting point is this right here. That's the starting point. Now notice that in 3 dimensions, we actually have to tell the starting point as a point, x, y, and z. So x1, y1, and z1, you have to imagine this floating in space here. And then, so that's your starting point. It's floating somewhere out here, I guess, or it's actually right there. But there's your starting point, and then the direction is actually this stuff right here. That's the direction. So that would be the vector A, B, C. Once you have those two things, a point and a direction, you can imagine extending the line in both directions. So this line, let me use a highlighter, sorry. So this line goes all the way back and all the way forward. So there's my line. Okay, so that's the way we're going to represent lines in 3 dimensions. So unfortunately, you have to use a set of 3 equations. We can't just use a single equation like we do in 2 dimensions. So let's go ahead and take a look at an example. Normally I would do this asking you to come up with your 3 points on the line, but it's just me in here, so I guess I'll be doing it. So name 3 points on this line. So let's go ahead and take these. And to get a point, what you do is you pick a value for t and then plug that into the line. And you'll get an x, a y, and a z. So let's go ahead and pick the value 0 because that's easy. When you plug 0 into these 3 formulas or these 3 equations, I get 1, 3, 2. Pardon me. Sorry. Yeah, hopefully it's not the COVID. Okay, but getting back to this. Suppose I plug 1 into this. Then I'm going to get x equals 1 plus 2 times 1, which is 3. Y equals 3 minus 1, which is 2. And then z is equal to 2 plus 3 times 1, which is 5. Let me just do one more. It says 3 points. Let's pick the point, how about -7, just to be different. So whenever I do this in class, usually everyone just picks simple numbers, but then I always get some goofball that'll pick like pi or the square root of 3. I'm just going to pick -7 though. So plug -7 into this. 1 plus 2 times -7 will be -13. 3 minus -7 is +10. And then 2 plus 3 times -7 is going to be -19. These are all points on this line. If I were to draw them in 3D, you would find that they all line up in a straight line, hence the name line. So what direction does this line point? Well, if you remember this here, these coefficients tell the direction. So the direction is in this direction of this vector. So remember this here, if I can get it to work for me, these three numbers will be a starting point for the line, and then these three numbers, and in the case of the middle number, it's -1, those three numbers provide the direction of the line, kind of like your slope and your y-intercept. So just to be clear, because this shows up in your homework, there is a difference between symmetric and parametric form of a line. So here is the difference, and for some reason, the PowerPoint is not producing all of the symbols. So this is the parametric form of a line in 3 dimensions. Sometimes this will be written in what's called vector function notation, and you'll get used to vector function notation because we're going to be dealing with vector calculus, and we need vector functions to do that. So don't fret. The main thing here is that you'll notice that in this case we have the x coordinate shows up here times I, then the y coordinate shows up here times j, just like you'd expect, and then the z component is times k. That's it. By the way, the I, J, and K are just placeholders. They're just there to let you know which component is which. You could have done this just as easily using these component notations without I, J, and K. Okay, so that's that. Now I need to doctor up this next one as well. Here we are. And this and this. So where did all this come from? Well, this came from taking this stuff and solving this for t. So if you solve this for t, you actually get this. And then if you solve this one for t, you get this thing, and that if you solve the last one for t. Anyway, so since they're all equal to t, you just set them all equal to one another, and you get what's called the symmetric form of the line. Not as useful, but it shows up in some of your homework, and I can't disentangle the two in WebAssign. So you can blame it on WebAssign. I don't like WebAssign. I don't know why you guys do, but there it is. So in all three cases, in all three of these, the direction that the line is going is ABC, it's a vector. And the initial point, and I put that in quotes because there is no initial point. The line stretches infinitely both directions, but we'll just call that x1, y1, z1. So one more of these, and then we'll see, take a break, and we'll do planes next. So we're finding the equation of line that passes through these 2 points. Now to make a line, we need a point and we need a direction. So I can pick either of these to be my point. So let's just pick this one for the sake of consistency. It doesn't really matter. Now I need a direction. The direction will point from one point to the other. So the direction will be a vector, and I'm going to use this vector that is formed by subtracting the 2 points. So 2 minus 1, 1 minus 1, and then 5 minus 4, which is the vector 1, 0, 1. Now let's put this all together. I get x is equal to, and I'm going to use this first point, so 1 plus 1t. Y is equal to 1 plus 0t, and z is equal to 4 plus 1t. So notice once again, I know I'm harping on this. Here's my point, my initial point, and notice that that's these 3 numbers here. And then I've got my vector. Whoa, come back. And the vector is this vector here, tells me the direction, and I've got that right here. And of course, when I write this, I could just eliminate this part right here because 0t is just 0. It's still there, it's just not there. All right, so we'll take a little break and then we'll do planes.